Where we left off last time was with this board designed, manufactured, tested. So this is all done. And we had the power supply designed but not made. So let me do that real quick. So this is just a standard power supply, standard split supply. Power comes in here with the center tab, goes through a bridge rectifier, goes through capacitors, goes to regulators, and then here this is just a voltage tripler, I think I designed. Although this is one for center tab, so you have the 3 lines going in, and then you get high voltage reference to center tab out. So that's all that. That works fine. Got plus minus 15 here and about 120 up here, which is more than enough for the tube buffer. So the only thing left to do really is building the output amplifier and building the actual output circuitry. And to do this, we'll start with our signal board, like this. This is this board with its 6 outputs. And then there's also the power supply board. Here this is power. And this goes down here to the signal generator board. I'll just write sig gen here. And from that we'll get 6 outputs, and I'll draw these like this. But these are all different levels. The lower frequencies are a little lower in peak-to-peak voltage, and the higher ones are a little higher. This is just an artifact of how this is designed. So what we'll need to do is we somehow have to equalize that, and we'll use a variable resistor for this. So 6 variable resistors. And then we'll feed this into a switch. Each of these 6 lines goes into a switch, and the switch looks like this. That it has 6 different contacts here. This looks like they're all connected, but 1, 2, 3, 4, 5. But they're really not. These are all individual contacts connected to these 6 lines here. Then on the other side, it has ones that are actually joined. And then in between that, it just has a contact like this that can go up and down. What this looks like is one of these sort of wafer switches. You might have seen them before. These just have a wiper that basically goes round, and wiper is down there. That connects this pin through this wafer in the middle to this output pin here. And these are all common together for one side. This is a dual 6 position, so it has 12 on the outside and 2 on the inside. And this connects to the 6 on this side, and this connects to the 6 on this side. And there's always 2 connected as you rotate this around. But the principle is these are all common together, and then you've got 6 on this side to choose from as you rotate this around. This is not as common a component as it used to be, but it's still very useful for things like this. So this goes then, the command line, which is connected to one of these at a time, goes then into a fixed gain amplifier. I'll just write amp. And because we have these 6 pots here, you can equalize the level, the output of each of these signal generators. And because you have a fixed gain amp, if you feed the same peak-to-peak voltage in, you multiply this with a fixed gain, if your amplifier actually has fairly uniform gain over the frequency spectrum that we're looking at here. But it should be all right. We can build it so that it's reasonably close. And if not, you can just bump the signal out up here a little, so that the output of this is always, let's say, I don't know, 20 volts peak to peak, whatever you want. So this is nice having this trim adjustment here. And then what you do is you feed this into another resistor, and this is your output level control. So if you want 1 volt peak to peak, you'll just turn this all the way down. If you want a full 20 volts, you turn this all the way up, and then this goes to your output. So we need to put this on a board, and as said, I'm going to build a vacuum tube amplifier here for this block, but you could just as well use a MOSFET or a JFET or a transistor. I'm going to use a vacuum tube because I like vacuum tubes, and also and that's really the only reasons why you would do that. This is, if you build a vacuum tube amplifier, it's probably going to be more robust if you feed in voltage back through here, although you probably burn up this potentiometer first anyway. But yeah, so let's actually look at the circuit that I came up with. Here's the circuit that I came up with, and we'll just go through this. These are our inputs from signal generator. These are the adjustment pots that I just talked about. And then we've got this wafer switch, this one. Up here, as said, each line connects to this output in one position. And then we go through a capacitor into our vacuum tube amplifier, and this is just very much a standard configuration. We've got our anode resistor here, we've got our cathode resistor here, so it's cathode biased. We've got our grid resistor here, and the values for these are 1 meg here, 68k here, and I think a k here. So, but you'd have to look at the datasheet yourself if you want to build something like that. One thing to note is I've got 2 resistors here in the filament line, and this is AC filament. So I think we can afford the extra distortion here. This is not a preamp or anything, where it's really important to get the filament hum out of this. So I've got 2 resistors here just because on my transformer, the only winding I have is a 12 volt winding, and this needs a 6 volt heater. That's what the E is for. So I'm going to waste effectively half my power. And since this is about a watt that I'm burning up here, I put 2 resistors so I can use a standard half watt resistor without having any issues. You could just as well combine these into one 1 watt resistor, but at the value that I need here, I only had half watts. So I put 2 here, and these are, I think, 18 ohm. And finally, to clean up the power from the voltage multiplier, I've got a regulator tube here. This is a 85 volt regulator tube, and this is a 30k resistor as a dropper. I might reduce this down if I notice that at the output here I don't get enough current. You could supply the tube with more current if you bump this down a little. But it should be fine, because the output from this, you won't get much current from here. The output is basically meant to be connected back up to a vacuum tube grid, which has a very, very, very high impedance. And then we've got our output coupling cap here. And these are 22 bipolar. bipolar. It's important that you use bipolar caps. You could just as well use a non-polarized one, but you'll be. It's very hard to find 22 microfarad bipolar caps, but you could go down a lot lower than this. This is a lot. It will probably work just as well with 1 microfarad, and that you could definitely get as a bipolar cap, as a non-polarized. But I used bipolars, which is just 2 electrolytic capacitors connected back to back, and that makes them go non-polarized. So this is basically a schematic for this, and here's the manufactured board. You can see the array of potentiometers down here. You could just as well use trim pots, but I used those because I had them lying around. One thing that's a bit annoying is these are obviously meant to be rotated from this axis, so you have to sort of get in there. But it's easily enough to do if you have a tool, like a scalpel. You could just go in there like this, or a screwdriver. You really don't have to use a scalpel. You could just as well use a screwdriver. Go in there like this, rotate it around. But especially if you're into reverse engineering, scalpels are really useful for scratching away solder mask or cutting tracks or stuff like that. So these are the potentiometers to adjust the level. These are the inputs. We've got the connections for the wafer switch up here. And as you can see, I hardwired this to one position for testing, and this is this one. We've got the 2 vacuum tubes here, the resistors and the bipolar electrolytics. And then we've got power input and output. We've got power, heater, and output here. And the resistors that are associated with that. So I think it's time we put this thing to the test. And then the only thing left is for me to make a case for this and then put it all in nicely, and then we'll have a signal generatory thing. So let me just hook this all up, and we'll have a little look at the oscilloscope. So I've got the camera focused on the oscilloscope here, and channel 1, the one as you see on the screen, is hooked up to the output of the triode gain stage, and for convenience in testing I also hooked up the signal generator board and the switch to the amplifier board. So I have it at the lowest setting, which is about 15 Hertz at the moment. So let me just switch this on. And this will take a second as the triode warms up. And there's our 15 Hertz. I mean, this is not really a sine wave, but we saw in the previous video that as the frequency gets lower, these the waveforms just degrade in quality. But this will be alright enough to do some basic measurements. We can also see the peak-to-peak voltage is about 36 volts. I think I want to have an average of 40 volts peak-to-peak on all of these channels. So I'll just turn the input trim pot just a little bit. Oh yeah, that's already at maximum. I can't actually get that any higher. So this will have to stay at 36 volts. I might I tweaked the feedback pot a little. Maybe we can get this. Yeah, this looks more like a sine wave. Now it's down to 20 volts, but at least it looks like a sine wave. So we'll flick over to the next one. And there we can see our 68 Hertz setting. This looks pretty good. It's 43 volts peak to peak, so that's fine. There's the next one at 1.7 kilohertz. This was supposed to be 1 kilohertz, and I might adjust the resistance later on, because this is not all that close to 1.7 to 1 kilohertz. You can see there's some slight jitter on there. It's 50 volts now, so I'll turn this down just a little bit. There we go. But this looks all right enough. And now the next, which is 4.3. It's also a little low. I can also just turn it up a slight bit. No. Oops, that was 2 positions. This is our 10 kilohertz setting, and if you look at that, not only does that look a little distorted, it's also way low. So I'll turn the input signal up here a little till we are at 40 volts, and now you can see it looks much more like a sine wave actually. And the last setting is 20 kilohertz, and this looks perfect and is at 40 already. So that works just as I expected it would work. Very nice. Has these 6 settings, and you can just flick through them. So the last thing to do is actually putting everything in a nice case, making a front panel, and that's what I'll do now. So next thing I did was mount this just on a little baseboard with the transformer, the power supply board, and the signal generator board, and this is hooked up via this loom to the amplifier board with all the pots here, and then also the wafer switch, which also connected via this loom. Here's the anode supply, and this is the filament supply, which is just braided for less interference, although this is not great. This should be going all the way around. But then again, there is a large path through these resistors that also not. So I don't expect much interference from this anyway. As you can see, I wanted to keep this a little more compact than other projects, which means I mounted these boards vertically and this one horizontally, because it doesn't really save you much space because the tubes are sticking up all that high anyway, and especially if they have their shields on, which they'll have once I mount this properly. You can see there's really not much to be gained. This is almost as high as this anyway, so you'd use just as much vertical space if you mounted this on its side. So for the front panel, I printed this piece of plastic here, which we're going to have the wafer switch. It's going to have the wafer switch here in the middle, power switch and power LED up here. Then down here the output pot, which will let you just adjust the output. And then I'm also going to have a couple of banana jacks up here, which I'll probably connect to the 15 volts power supply here, so you can, if you're not using the signal generator function, you can use it as a power supply, which is nice. And then here the output jack. So this goes on here just like this, and then this is screwed down, and then the rest of the case, which is going to be like a shell this way, is just going to drop over this and mount to these posts here, which conveniently have holes in them for doing that. So I'll assemble that, and then this project is basically done. So here's the thing put all together. I printed a little knob and made a bit of a front panel. I mean, never mind me cutting it very accurately here. It's, by the way, it's missing the power supply jacks here. I will install those later. But signal generator is working, and there's the level pot, which you can regulate it up and down. And then here's the switch that lets you select the frequency. Here's the output, and then there's on a little power LED that's just run off the 30 volt, the plus minus 15 volt supply directly. So yeah, I'm pretty happy with this project, and yeah, it's done now. So I have a indestructible signal generator for just feeding a test tone into a vacuum tube amplifier.